Okay.
Today we have Andrew, and he's going to talk about LLT polynomials. Thank you for coming.
That's what I'm saying.
Yeah, so thank you for inviting me to speak. And thank you all for coming. I'll share my screen. Okay, yeah, and as Slava mentioned, I'm going to be talking about a vertex model for LLT polynomials. So this is based on joint work with Sylvie Corteel, David Keating, and Jeremy Meza, and all of us are from that university across the bay, UC Berkeley. Okay, so my plan for today is first I'm going to give some background. We're going to review a vertex model for sure polynomials, and hopefully that'll get our hands dirty with creating vertex models for certain polynomials. And then we're going to extend that vertex model into our vertex model for co-inversion LLT polynomials. Once we have that vertex model, I'll use the vertex model to prove some results about LLT polynomials. And then in the last section, I'll talk about some work that we've been working on with supersymmetric LLT polynomials that could be directions for future research. Okay, so first we're going to go over a vertex model for sure polynomials. There's a pretty famous bijection between semi-standard skew-Young tableau and non-intersecting upright lattice paths. So the idea is that every row gives you a path in the lattice. So for example, if I look at the bottom row here, that corresponds to the rightmost path in the lattice. So this one over here. And the entries of the row are exiting instructions. So every time I see a number, I exit a column to the right in that row. So this one tells me that I exit the column in row 1. This one tells me that I exit the column in row 1. This 3 means I exit the next column in row 3. And this 5 tells me that I exit in row 5. Okay, so I can do this for any semi-standard skew-Young tableau. The partition lambda gives me the top boundary condition, so it tells me where the paths are exiting the lattice. And the partition mu gives the bottom boundary condition, so it's telling me where the paths are entering the lattice. And n, the maximum entry you're allowed in your tableau, has to be the number of rows. Okay, so there's a bijection between semi-standard skew-Young tableau and non-intersecting upright lattice paths. And I'm going to use that to construct a vertex model for sure polynomials. I'm going to assign every box, every vertex, a weight. So the weight of a box is x sub I, where I is the row that you're in, if a path exits to the right in that box, and it's going to be 1 otherwise. And then the weight of the entire configuration is just the product of the weights of all the vertices. So in our running example, you can see that we have 2 boxes, namely these 2 down here, that contribute an x1. So a path is exiting to the right in row 1 in those 2 boxes. And that's why I have an x1 squared over here. Okay, and if you compute the weight for this entire lattice configuration, you end up getting this weight. Okay, and then the partition function for the vertex model is the sum over all valid configurations of the weights of that configuration. And it's pretty easy to see that's just the Schur polynomial of lambda over mu. So this is what I mean when I say that this is a vertex model for the Schur polynomials. Okay. So next up, I'm going to extend this vertex model into a vertex model for LLT polynomials. By the way, if you have any questions at any point, feel free to stop me and ask them. But we're sort of entering the heart of this presentation. So I'm going to extend the vertex model for Schur polynomials into a vertex model for LLT polynomials. Okay. So before I do that, first I should tell you a little bit about LLT polynomials, their history and their definition. They were introduced by Lascoux, Leclerc, and Thibon in 1997, hence the name LLT. And their original definition was in terms of semi-standard ribbon tableau, where you Q-count a spin statistic. In 2005, Haglund, Heyman, and Lohr gave an alternative definition where you think of the LLT polynomials as a generating function for tuples of semi-standard Young tableau, and you Q-count an inversion statistic. More recently, a tweak to that definition is to count co-inversions instead of inversions. And then, so that co-inversion version is the definition I'm going to be using throughout most of this talk. And what we're going to do is we're going to formulate the LLT polynomials, the co-inversion LLT polynomials, in terms of upright lattice paths. Okay, so this is the co-inversion definition of LLT polynomials, and this is the definition I'll be using throughout the rest of the talk. So the idea is you sum over all semi-standard Young tableau for each of the skew partitions individually. The x power is just x to the power of that tableau. And the t power is the number of co-inversions in that tableau, where a co-inversion triple is given by 3 boxes in the diagram, A, B, and C, where in order to weakly increase, you go around counterclockwise. So if you have a triple in the diagram and you go around counterclockwise, the entries should weakly increase, A to B to C. Okay, so for every tableau, you count the number of co-inversions, and that becomes your power of t. And then the entries give you the power of x. Okay, so I mentioned that there are other ways to define LLT polynomials, so I want to take just a moment to talk about those other definitions. So the inversion LLT polynomial is, instead of co-inversions, I count inversions of the tableau. And an inversion triple is the opposite of a co-inversion triple. It's all the triples that are not co-inversion triples. The two are related just by messing around with the powers of t. So all of the results I prove for co-inversion LLT polynomials in this talk, you can translate them into results about inversion LLT polynomials. Okay, going even further back in time, the very first definition of LLT polynomials was in terms of semi-standard ribbon tableau. And the relationship between our definition and the semi-standard ribbon tableau definition is through the Littlewood quotient map, which gives a bijection between semi-standard ribbon tableau and k tuples of semi-standard Young tableau of the given shapes. So just to give you an idea of what this bijection looks like, if I give you a partition lambda and you want to compute the tuple of diagrams that correspond to that partition, what you can do is you can label the boundary of your partition with the numbers from 0 through k-1. And then you look at all of the boxes in the diagram where the row and column are indexed by the same number. So for instance, here k equals 3, and these black boxes are all the ones where the row and column number are 0. And then I combine all of those boxes together, and that becomes the first, or the 0th partition in the tuple. Okay, and same thing for the blue triangles and red circles. Okay, so that gives me a way to associate to every partition a tuple of partitions. And then the Littlewood quotient map gives me a bijection between ribbon tableau and semi-standard Young tableau on those shapes. And the idea is you look at the southwestern most box of all of the ribbons and look at their content modulo k, modulo 3 in this case. So for instance, on all of these gray diagonal lines, those are the cells with content 0 mod 3. And you can see that the 1, the 3, and the 8, 2, 11, and 12 those ribbons all have their southwesternmost box on a gray line. So the content is 0 mod 3, and that becomes the filling of the 0th tableau in my tuple. Okay, and same thing for the blue and the red. Okay, so overall, the Littlewood quotient map gives me a bijection between semi-standard K ribbon tableau and semi-standard Young tableau on the K tuple of Tableau. Okay, so back to defining LLT polynomials. The spin statistic is going to be what gives us our power of t. And the spin of a ribbon tableau is just the sum over all ribbons of the height minus 1. So in our running example, you can see that this ribbon has a height of 3, so the height minus 1 of that ribbon is 2. This one has a height of 2, so its height minus 1 is 1. Add up all the height minus 1s of all the ribbons, and in this case, you get 14. And that's what the spin is. Okay, and I guess one thing to note is that the spin does not depend on the actual filling of the ribbons. So in a semi-standard ribbon tableau, you fill in all of the ribbons with numbers, but the spin doesn't actually depend on how you assign the labels to the ribbons. Okay, and so with all that, finally, here's the definition of the LLT polynomial in terms of ribbon tableau. So I sum over all semi-standard ribbon tableau of lambda over mu. The x power is just given by the entries of the tableau, and the t power is given by the spin. Okay. And again, there's a relationship between this version of the LLT polynomials and the co-inversion LLT polynomials that I'll be using throughout the talk, just by, again, messing around with the powers of t. Okay, and I should mention, Curran, Joost-Wolff, Zhang, and Zhang actually used this definition of LLT polynomials to construct a vertex model that's similar to the one that I'll be constructing in a second. Okay, so now that you know what an LLT polynomial is, let's try to construct a vertex model for them. So the idea is that LLT polynomials generalize Schur polynomials in the sense that if I ignore the powers of t, if I set t equals 1, the LLT polynomial is just going to be a product of the Schur polynomials. And in terms of the vertex model, what that means is that if I have a configuration for each of the skew partitions individually, and I superimpose them, then I get a vertex model for the LLT polynomial if I ignore the powers of t. So for instance, what I'm saying is every time a path exits to the right in row I should pick up an xi, and I should do that for each color individually. So for example, that box, both red and blue are exiting to the right, so I should pick up an x1 squared from that vertex. And then if I do that for every single box individually, that'll give me the weight of the configuration, and the partition function for that will be the LLT polynomial with t equals 1. Okay, so we have a vertex model that works when t equals 1, but we sort of need to put t back into the vertex model. And the way we do that is we allow the colors to interact with each other. So again, for one color, every time a path exits to the right, we pick up an x sub I, where I is the row that you're in. And in order to introduce t, I'm going to say not only do you pick up an x, but you also pick up an x times t to the delta, where delta is the number of colors greater than that color that appear in the vertex. So every time a color exits to the right, you pick up an x, and you could also pick up t to some power. Okay, so for example, blue is going to be color 1, red is going to be color 2. These are the 8 configurations in a vertex that give me a t. And so what gives me a t is blue exiting right and red being present. So for example, this vertex, blue exits right and a larger color, namely red, is present. So that gives me an x times t from the blue. And then red is also exiting to the right, but there are no larger colors present in the vertex. So I just pick up an x. So overall, this vertex gives me an x squared times t. And similarly for the other 7 vertices that I have here. Okay, and again, the weight of a configuration is just the product of the weights of the vertices. In our running example, these vertices that are bolded are the ones that give me a t. So overall, I have a t cubed as the weight. Okay, so that's the vertex model. So why does this vertex model give me LLT polynomials? Well, it's sort of by design. The way that we chose the powers of t correspond exactly with co-inversions. So for instance, if I have a co-inversion triple A, B, and C, what that means is that, well, this B tells me that there's going to be a blue path exiting the column in row B. So if I look at this box, there should be a blue path exiting to the right in row B. And then the fact that these two boxes are in the second tableau means that a red path is entering the column in row A and exiting in row C. And in the middle, it sort of has to pass through row B. And so what I'm getting at is that every co-inversion triple corresponds to some instance of a color exiting right and a larger color being present. So, which is exactly what gets us a power of t in the vertex model. Okay, so hopefully that convinces you of this theorem that the vertex model we just constructed, the partition function for that vertex model is exactly the LLT polynomial. Okay, now's a good time to stop just briefly for any questions. Are there any questions? Okay, if you have any questions, let me know. Now that we have the vertex model, I'm going to use it to prove some things. And our main tool in this regard is going to be the Yang-Baxter integrability of the vertex model. And so what that means is that I have some R matrix, which I'm going to denote with this sort of cross vertex. And in the presence of the cross vertex, the vertices that we just constructed commute with each other. So specifically, this equation. The sum over all valid configurations on the left-hand side equals the sum of all valid configurations on the right-hand side, where I've moved the R matrix from the left to the right, and I've swapped the X and Y. Okay, so what is this R matrix? It's given by these weights. So for one color, these are the weights. And then for K colors, the colors can interact with each other. Instead of Y over X, I have Y over X times T to the epsilon, where epsilon is the number of colors greater than I of type 1. So for example, if we look at this second configuration over here, both blue and red have type 1. So blue has type 1 and a larger color is also in the vertex and has type 1. So that's why I pick up a 1 minus Y over X times T. And then red, there are no larger colors in the vertex. So I just have a 1 minus Y over X. Okay, and then the Yang-Baxter equation, one of the things it says is that if I assign these boundary conditions on the left-hand side and the right-hand side, and then sum over all valid configurations, I should get an equality. And you can check that indeed these two things equal each other. So I won't go through the proof of the Yang-Baxter equation. It's pretty complicated, but there's some induction argument that you can do on the number of colors. Okay, but now that we have the Yang-Baxter equation, we can use it to prove some useful things. The first thing that you get almost immediately is the fact that the LLT polynomials are symmetric. So this is a very well-known fact, but this is yet another proof of it. And this argument is often called the train argument, because the idea is that you can take one of our R matrices and push it through the lattice until it pops out on the other side. And you'll notice that what we did is we swapped xi and xj with each other in the process. The only valid configuration of the R matrix with zeros on the left-hand side is just all zeros. And same thing over here. So the only valid configuration of the R matrix with zeros on the right-hand side also has zeros on the left-hand side. And these two vertices have a weight of 1. So what this gives you is that is this bottom equation down here. So xi on bottom, xj on top equals xj on bottom, xi on top. And using this process, you can swap any two of the x's that you want to, and that's enough to show that the LLT polynomials are symmetric. Okay. So it turns out that you can use a similar argument to prove a Cauchy identity for the LLT polynomials. But before I get into the nitty-gritty of that, I want to introduce a new vertex, which I will call the L star matrix and draw with gray boxes. And it's related to the white vertices, the L matrix, that I introduced in a previous slide. So all I do is I do a little change of variables and then multiply by a power of x and a power of t. To be more explicit about what the weights are, one way to think about it is, again, every color contributes a multiplicative factor to the overall weight. And the formula is given by these expressions. So alpha I here is the number of colors greater than I of type 1, 4, or 5, and beta I is the number of colors greater than I of type 4 or 5. So this recipe gives me a way to assign a weight to all the gray vertices. Okay, back to the Cauchy identity. What we're going to do is we're going to use the train argument n squared times. So I have n squared R matrices on the left-hand side here. And then I'm going to use the Yang-Baxter equation to push them through to the right-hand side. One thing to note, there's this power of t in front of the LLT polynomials. That power of t only depends on lambda. And I guess the more important thing to note is that these are semi-infinite lattices. They're infinite going off to the right-hand side. So that'll be important in a bit. Okay, the reason that the semi-infiniteness of the lattice is important is that it sets certain boundary conditions on the colors. So for the white vertices, for the L matrices, a blank white vertex gives me a weight of 1. So if I send a blank vertex off to infinity, that just gives me a weight of 1. If I have a horizontal path, that gives me some power of x and some power of t. And so if I send that vertex off to infinity, that gives me an x to the infinity, which is 0. So in other words, one way to think about it is this is not a valid configuration because it'll give me a weight of 0. The opposite is true for the gray vertices. So a blank gray vertex gives me an x power. So when I send a blank gray vertex to infinity, I get 0. And then if I have a horizontal path, that has a weight of 1. So if I send that off to infinity, I pick up a weight of 1. And so what that means is, in terms of the left-hand side configurations, because these white vertices and these gray vertices are off at infinity, the only way to put the paths in the configuration is to have all the paths in the gray vertex go off to infinity and no paths in the white vertices. Okay, so this is the only valid configuration on the left-hand side. You can compute what the weight of this is, and it ends up being this expression. Okay. Excuse me. For the right-hand side, things are slightly more interesting. So again, the gray vertices, you have to send particles off to infinity. For the white vertices, you can't send any particles off to infinity. And so what that means is that the paths sort of have to start down here, end up, so they start in the bottom left, travel somehow to the upper right, and then go diagonally down across the R matrices. And if we split based on what happens on the boundary between the gray and the white vertices, we get a sum of 3 terms. The first one is just our vertex model for the LLT polynomials. The second one is a little bit harder to see, but it ends up being an LLT polynomial times some x's and times some t's. And then the weight of the last term ends up being this expression. Okay, so overall, if you evaluate the left-hand side and right-hand side and rearrange the terms, you get our Cauchy identity. Okay, so in the final section of this talk, I'm going to talk about purple vertices and try to extend our vertex model to supersymmetric LLT polynomials. And this is sort of an ongoing research project that we're working on. But first, I should talk a little bit about the work of Agarwal, Borden, and Wheeler. What they did is they had a more general vertex model than the one I presented today. More general in the sense that it specializes, it has many interesting specializations, including the L and R matrices. And using this vertex model, they were able to independently derive many of the results that I've covered. But the vertex model also has other interesting specializations, including an L prime and an R prime matrix, which I'll introduce shortly. And what I'm going to do is I'm going to use those 2 specializations to prove some results about LLT and supersymmetric LLT polynomials. Okay, so now I'm going to introduce the purple vertices, or the L prime matrix. There's sort of a nice geometric interpretation of the purple vertices in terms of the white vertices, namely take the white vertices and then invert the vertical parts of the paths and reflect the paths over the y-axis. So just as an example, let's take a look at what's going on over here. So I start with that path. I invert the vertical parts. So where there was a path, there's no longer going to be a path. And where there isn't a path, I'm going to put a path in on the vertical parts. So I get this. What I'm saying is there's no path up here, so there should be a path up here. There's a path down here, so there shouldn't be a path down here. But I don't touch the horizontal parts as of yet. And then I take this path and reflect it over the y-axis. So I get this. Okay, and that's how to get from the white vertices to the purple vertices. Okay. So to be more precise about what the weights are, 2 configurations give me an x. And so just as before, I pick up an x when a path exits to the right, and I pick up a 1 otherwise. For k colors, the colors interact with each other. Instead of picking up an x when I exit to the right, I pick up an x times t to the delta prime, where delta prime is just the number of colors greater than that color that are vertical at the vertex. Okay, so this is how I define the purple weights. And Agarwal, Borden, and Wheeler proved that these purple weights give me a partition function associated to the conjugate LLT polynomial up to some power of t. So here, when I talk about conjugating a tuple of partitions, I mean conjugate all the individual partitions and then reverse their order. Okay. They also showed that the L and L prime matrices together satisfy the Yang-Baxter equation in the presence of a yellow vertex, which is the R prime matrix for the model. What are these yellow vertices? They're given by this formula, and again, the weights are functions of y over x. So for one color, these are the weights. For k colors, instead of y over x, I look at y over x times t to the epsilon prime, where epsilon prime is the number of colors greater than I that appear in the vertex. So everything of types 1, 2, 3, or 4, but not of type 5. Okay. They're also able to use the Yang-Baxter equation to prove a dual Cauchy identity. And I won't run through the proof, but it's similar to the train argument that I showed you before. And you'll notice that instead of you sum over lambda and you have L associated with lambda and L associated with lambda prime, which is why it's called the dual Cauchy identity. Okay, but really what I want to talk about is the application of the purple vertices to supersymmetric LLT polynomials. And in order to define these, I have to talk about super ribbon tableau. So I'm going to use the ribbon tableau definition of LLT polynomials that I talked about at the beginning. So what a super ribbon tableau is I take a ribbon tableau and I label the ribbons with regular numbers and primed numbers. I enforce that all the primed numbers are bigger than all the unprimed numbers. And then I put certain demands on the ribbons. Namely, the primed ribbons have to strictly increase as I go across the rows. And going down a column, all the unprimed ribbons have to strictly increase. So normally, if I didn't put these conditions on, all I would require is that the ordering weakly increases. But I put these two extra conditions on. Across rows, primed ribbons have to strictly increase. Down columns, unprimed ribbons have to strictly increase. The supersymmetric LLT polynomial is then defined by summing over all super ribbon tableau. The x weight, or the x power is given by the primed weight, or sorry, is given by the unprimed weight. The y power is given by the primed weight. And again, the power of t is just the spin of the tableau. So that's the definition of supersymmetric LLT polynomials. And I'm going to abuse notation a little bit. If I have a tuple of partitions, I can define the super ribbon tableau associated to that tuple just by via the Littlewood quotient map. The Littlewood quotient map gives me a bijection between lambda over mu, a partition, and bold lambda over bold mu, a tuple of partitions. Okay, so it turns out that the purple and white vertices form a vertex model for the supersymmetric LLT polynomials up to a power of t. Namely, if I look at all configurations with white vertices on bottom and purple vertices on top, and then I sum over all valid configurations, that will give me the supersymmetric LLT polynomial. We also have a way to convert between the purple and the white vertices, namely inverting vertical parts, reflecting over the vertical axis. That process lets me convert a white vertex to a purple vertex. And so that dual relationship between the purple and white gives me an identity relating supersymmetric LLT polynomials to each other. Namely, if I conjugate lambda and mu, and I swap x and y and then mess around with the powers of t, those two things are going to be equal to each other. Okay, and again, I won't go through the proof here, but the idea is to use the fact that you can convert purple and white vertices into each other. Okay, and that's all I had. So thank you all for listening. And if you have any questions, you can ask them. Yeah, I realize we have quite a bit of time left.
So Thomas Lamb gave a definition of supersymmetric LLT polynomials, but there was one difference, which was that his alphabets, the primed and the unprimed, alternated. So they weren't. So you had 1 is less than 1 prime is less than 2 is less than 2 prime. Have you seen that definition?
Yeah, I have. So I don't know if we're thinking of the same paper, but what Lamb does is actually pretty general, where he allows basically any ordering on the two alphabets, as long as you like respect the ordering on the unprimed and the primed weights individually. So as long as like one prime is less than two prime.
Okay.
Yeah.
So I thought that okay, it wasn't obvious to me that it would be equivalent to make that change, but maybe it's straightforward.
Yeah. So yeah. So again, I don't know if we're thinking of the same paper by Lamb, but the paper I'm thinking of, his definition of super ribbon Tableau is pretty general. He just allows any ordering.
So let's see, and
oh yeah, this is the paper of Lamb that I'm thinking of, if that rings a bell.
That's probably the paper I'm thinking of. I'm not sure.
Okay.
So let's see. There were so we had some models that I discussed in 2 weeks ago, which produced they produced a special case of his super LLT polynomials, and we were I was reminded of that several times during the talk. So did you look at our paper?
Yeah, I have seen your paper.
Okay, so it was different from it was similar to yours in that the colored lines would enter at the top and exit from the bottom. We didn't use the colored lattice model technology then. We used something that was kind of equivalent. So when I gave the talk, I tried to translate it into the colored lattice model. Anyway, but our methods were different because instead of the Yang-Baxter equation, we made use of the operators on the Cauchy and Stern box space, which I suppose you could do too.
Yeah, it'd be interesting to like apply that methodology to this Vertex model, I guess.
Right. So that was what LLT originally did, I guess. Okay.
I'll put that on my list of things to investigate in the future.
Okay. And you don't have a preprint yet. You're working on it. Is that right?
Yeah. So I guess I have a preprint for, I guess, everything before this section. We don't have a preprint for the supersymmetric stuff that I just discussed.
Right.
So related to Dan's question about these more general supersymmetric LLT polynomials,
yeah,
where you can kind of intersperse the primes with the unprimes in any arbitrary way. This is what you were saying, right?
Yeah.
Yeah.
So I wonder if it would suffice, if you want to capture those, if it would suffice to intersperse the purples with the whites in the sort of the same way. Because as I understand, your purples are all stacked above the whites, but if you start to, which kind of corresponds to the primes all being above the unprimes.
Yeah. So yeah, go ahead.
I was going to say, but if you start to intersperse the primes with the unprimes, then maybe the thing to do is to intersperse correspondingly the purples with the whites.
Yeah, I think you're right. So like a row of purple vertices adds I'm gonna get this flipped, but it adds like a vertical strip, whereas like a row of white vertices adds a horizontal strip. So if you went like, as you said, if you went white purple or something like that, that would allow you to interchange the primed and the unprimes. Add a horizontal strip, add a vertical strip, add a horizontal strip, add a vertical strip. Yeah.
Yeah, thanks.
I think this is a prettier picture, but Yeah, so I think that would capture the, I guess, the generality of what Lamb did.
Thank you.
Do you have any quantum group interpretation of your solutions to the Yang-Baxter equation?
Yeah, so a lot of this talk was like mostly in the world of combinatorics. So there is a way to interpret these in terms of quantum groups. Yeah, in fact, to give credit to Agarwal, Borden, and Wheeler, they discuss this in a little bit more depth than we do in our paper. So I believe their vertex model is like a UQ SLMN vertex model, if I'm getting the notation right. So that's a long-winded way of saying yes. There's a way to interpret these in terms of quantum group representations. Yeah.
Is it that full generality, or do you specialize M to be 1 or something? Do you know, for your specific model?
Yeah, so for our, okay. Yeah, so again, there's, our vertex model is a particular specialization of theirs. Yeah, and I think everything that we do actually does live in this world. And I guess like our variable is t that I've been using, so maybe I should write ut instead. But yeah, there's a whole bunch of change of variables that you have to do in order to get our particular specialization. Again, that's a long-winded way of saying yes.
So I have a question, just I didn't completely follow everything with kind of inversion versus co-inversion. So is every LLT polynomial you're talking about, are those all co-inversion LLTs? Or some of the models for inversion LLTs?
Yeah, yeah. So every time you see a little script L in the presentation, that's a co-inversion LLT. Yeah.
Okay. So maybe I just didn't follow if they were all L's or if there were any G's.
Yeah, I think I tried to use only L's in the presentation, except when I was defining the other ones.
But
yeah,
can you use the same techniques? Like, could you, in the way that you took the co-inversions and mapped it into the lattice model, could you do that with inversions? Or was it specific to co-inversions that it worked?
Yeah, so I guess when we were originally trying to like find this vertex model, we tried to do the inversion version, but I guess you run into problems where like the powers of t get messed up, or the weights just become what's called non-local, in that like if I can get to it, like the weight of a vertex doesn't depend on just the configuration in the vertex, but it depends on stuff around it. And so eventually we realized that like from a combinatorial point of view, the co-inversions were really the thing we wanted to look at. Yeah. But again, as I said, like if you prove something about co-inversion LLT polynomials, that'll tell you about inversion LLT polynomials. You just have to mess around with the powers of t.
Yeah, I guess I was just wondering if there was some sort of gamma delta sort of, like, you have gamma ice and delta ice in certain contexts. And I was just wondering if this was one of those situations, or perhaps not.
Yeah, I don't think it is. Does anyone have any other questions for me?
I have a question, but it's sort of maybe not a fair question, but there was a comment at the beginning of LLT's paper as to why they were studying LLT polynomials. I mean, I guess it's not a question for you, it's a question for them, but they say that there's some connection with these polynomials with plusism for the power sum symmetric polynomials. I guess that's Adams operations. Do you understand what they meant by that? Yeah.
So I guess without actually looking at the paper directly, I don't understand what you're trying to get at.
I could show you the paper if I share my screen.
Okay.
Hang on, I have to find it. Oh, and I, of course, opened. Should be at the beginning of the paper. All right,
I guess, okay, I'm going to stop sharing my screen.
Oh, okay.
Just for a second.
Okay, I'm having trouble finding the words, so I'll search for plusism. Oh, I'll just read you what it says.
Okay.
So it's in the second paragraph of the paper. They say these objects, though unfamiliar, arise in several natural contexts. Their use is implicit in many classical algorithms related to the symmetric groups. In particular, they can be applied to the description of the power sum plethism operators, psi sub k or psi upper k on symmetric functions. So these would be what are sometimes called Adams operations.
Yeah.
And I just was unable to figure that out, and I thought maybe somebody knew. I can so what are they talking about here? So that was all. So anyway, it's not an important question, and it's not a question about your talk. So I didn't expect you to know the answer.
Symmetric functions.
Okay, so anyway, I propose we don't spend any more time on that.
Yeah. Sorry, I'm
So thanks for your talk. It was quite interesting.
it was my pleasure. Yeah, and I guess no one complains about leaving a seminar 5 minutes early. Yeah, but again, thank you for this opportunity to speak at this seminar.
Right.
I learned a little something, and hopefully you did too.
Great talk. Thanks.
Thank you.
Okay. I wonder if Slava is still here. Are we still recording?
Yeah. Oh, I think I have the power to end the recording.
Okay, so why don't you stop the recording?
Okay.